The title of my talk is in Math We Trust. But let me start with a story of starting from physics. So in physics, sometimes we discuss a problem when you have two electrical charges, for example. Even when they're far separated, they act a force upon each other. So this is a pairwise exchange among the particles, and they are described by something called the Coulomb's law. But later on, people find this description is a little bit inconvenient, just out of a matter of convenience and out of a matter of a philosophical prejudice. We say, why can these two particles interact with each other without even touching with each other? So we introduce a concept called a field. We say the very first particle generates an electrical field quite locally, and that the electrical field propagates to the other place, and then it acts on the second electrical charge. So therefore, the concept as a medium of exchange for electromagnetic force, which is the electromagnetic field, was born. But in the beginning, this was like a simple bookkeeping device. People don't know whether it really has its own physical identity or has its own intrinsic value. So by now, this example should sound a little bit familiar for you. The pairwise exchange between two particles is similar in comparison to barter exchange economy in a primitive society. People only exchange their goods pairwise. But later on, civilization invented a new medium of exchange, namely money. So you don't change goods for goods, you exchange goods into a medium of exchange, which is money, and then later was exchanged to another hand, from money back to goods. So this analogy, I think, is almost perfect. The pairwise exchange of particles is like a barter exchange, and the exchange through fields, the concept of fields, as a medium of exchange is the monetary system. But then the question comes whether the medium of exchange has its own intrinsic value, and if so, how do you price the value of the medium of exchange? Actually, most of you know about Einstein. You know about E equals to mc squared, but Einstein didn't receive Nobel Prize for writing down this formula, E equals to mc squared. He wrote down another formula for which he was awarded the Nobel Prize. And in our language of interpretation, we can basically say he discovered a pricing formula for the medium of exchange. Namely, what is the value of the medium of exchange in the natural world? The basic currency in the natural world is energy. So basically, he assigned a precise value of energy to the electromagnetic field, namely the formula E equals to h bar omega, and that was his Nobel Prize winning work. And that was one of the greatest revolutions in science. Suddenly, this concept, which was introduced in an auxiliary fashion as a convenient way of description, suddenly discovered its own intrinsic identity and its own intrinsic value. So now, in a monetary system, what is the value of the medium of exchange? Let's compare two possibilities of apple versus gold. But apple actually, let's, for the sake of argument, assume that the gold has no commodity value. It has some commodity value, but very, very small. But apple actually has some real commodity value. You can actually eat it, and you can prevent yourself from starving. So let's assume that the apple actually has more commodity value than the gold. But as a medium of exchange, apple does not have high value as a medium of exchange. Why? Because when you look at the curve from the left, by one apple, we mean very, very different things. Those who produce or consume apple maybe are in a better position to assess the quality of that apple. But as a medium of exchange, eventually you will go to in the hands of people who neither produce nor consume apple. And for them, it's very, very hard to assess the quality of one apple. So the concept of one apple has a very broad meaning to different people, and therefore, as a medium of exchange, it is not convenient because people cannot agree. Never mind what is the value, but they cannot agree what is exactly meant by one apple, because of course, over time, its value also degrades, so it changes as a function of time. But gold is very convenient because by 1 ounce of gold, we know precisely what is meant by 1 ounce of gold. And that contribution is again made by two great physicists. One is by Archimedes. You all know about the story of Archimedes, that the king commissioned him to discover whether the crown somebody fashioned for him is made out of real gold or not. And it was a really, really difficult problem. But one day he was relaxing in a bathtub, and in his eureka moment, he discovered a way to measure the crown, whether it's made out of gold or not, without breaking the crown apart or to melt it. Basically, to look at the levitating force inside water as he was sitting in. So that measurement of Archimedes gave us a way to precisely to measure the content of gold. So therefore, by 1 ounce of gold, we know precisely it's 1 ounce of gold, not of something else. The great physicist Isaac Newton, you all know about his great work on Newton's law of motion, on Newton's law of gravitation. But he, even after his great fame, he was still a poor professor. And the Queen Anne wants to do a big favor upon Newton and appointed him to the master of the royal mint. And he was in control in making the gold coin. So at that time, there's actually also less consensus about the value of a gold coin. Why? Because some people will just take a gold coin and rub it a little bit and then pass it on to another one. And after they pass on and rubbing enough times, they get an extra gold coin. So that's why then the value of what exactly is meant by one coin has a broad distribution, no consensus, and that is the problem as a medium of exchange. The medium of exchange, the value is in its small variance, its precise understanding of its value. So Newton actually introduced this method that he carved out these little stripes on the edge of a gold coin. So then if you rub it, it's very easy to discover. So the value of the medium of exchange lies in its consensus. This way, one gold coin means exactly one gold coin, and we know exactly it's made out of gold. So therefore, consensus has intrinsic value, because in the natural world, it's very difficult to reach consensus because of a fundamental law of nature, which is called the second law of thermodynamics. If on the picture on the left, you see all these little magnets, all these little compasses have reached consensus, they all point along in one direction. That is a state of the natural world, which we call a low entropy state. On the right-hand side, we actually have seen the random orientation of this magnet, and this is a state of the natural world, which is high entropy. The second law of thermodynamics states that left alone, the natural world will always tend to a disordered state with high entropy. On the other hand, the value of the medium of exchange lies in its consensus. Consensus has low entropy, and therefore it's very, very hard to reach. But it counteracts the second law of thermodynamics. So it can actually only reach that by dumping entropy somewhere else. It can reduce its own entropy, but then it has to dump entropy somewhere else. This is actually the secret of life. What is life? Life is an organized form. We're made out of atoms, we're made out of cells. All these are natural particles. But we're living in a state of reduced entropy, and because we dumped entropy somewhere else. So once you reach a state of reduced entropy, which is consensus, it's extremely valuable because it's very, very hard to do. It almost counteracts the second law of thermodynamics. But then how does the natural world do it? How does the natural world, without a central command center, reach consensus in a self-organized fashion? We actually have examples in the natural world. Every time when you stick a magnet onto your refrigerator, something magical has happened, because the magnet inside is made out of all these little compasses, which are the spins of the electron. But most of the time, their state of matter is on the right. They're in randomly disordered fashion, and they don't reach consensus, and therefore, actually, the magnet at high temperature is in this state, and they wouldn't stick onto your refrigerator. But at low temperature, a reduced entropy state is possible. These magnets can spontaneously organize themselves to reach a matter of consensus, and then it becomes very useful as a magnet. On the right side, you see a wonderful phenomenon in the biological world. We have single-cell bacteria, but they can communicate with each other by emitting some receptors. And if you receive enough receptors from your neighbor, you know that you are in a crowded situation. And then the bacteria, so this phenomenon is called quorum sensing. And then the bacteria can spontaneously decide to do something, for example, emitting light. And this is the behavior of a bacteria called Fischerei. So you see the natural world, without a central command center, in a decentralized way, in a self-organized way, can still reach consensus, but they do it at a cost. Namely, they have to dump entropy somewhere else. So now let's move into the world of distributed computing. So let's first imagine whether it's possible to have a master program which can coordinate among all these different computers, and then you can reach consensus at almost no cost. So there's a theorem in computer science called Fisher-Lynch-Patterson theorem, and it states that this is not possible. But in a physicist's way of viewing this result, you can think of this master program which can reach consensus without any cost as an object which we call Maxwell's demon. It has the capability of reduce entropy without any cost and to make the world more organized without any cost, and this is not possible. So the Fisher-Lynch-Patterson theorem is very much in spirit like the second law of thermodynamics. So therefore, we come to the conclusion that we actually have to have a system which is based on randomness so that we can organize them ourselves better, but by reaching consensus, but by dumping entropy somewhere else. Now, this is really the essence of the very first protocol in the blockchain, and namely the Nakamoto consensus. Because we reach consensus by computing a hash function, but by computing a hash function through proof of work, we have the dumped entropy somewhere else. So this is very similar to what's happening in the natural world. So this, therefore, once this protocol is discovered, it reached a new era in the networking world, but also I think it reached a new era in the human civilization. When you look at the history of the world, and in particular, when you look at the history of the networking world, it can be described as an oscillation, periodic oscillation, between centralization versus decentralization. In Chinese, I would call it 分久必合，合久必分。世界的历史就可以用这个8个字来表现。So in the early days of circuit switching, it's a centralized protocol, and only centralized entities such as AT&T can monopolize all networking resources. But once a decentralized protocol as TCP/IP has been discovered, immediately the monopoly of AT&T is destroyed. So we reached a way from centralization to decentralization. But then the content on the web become very, very fragmented. So somebody has to do the job in organizing all these contents, and that fall onto the task of some centralized entity, such as Google and Facebook. But now, with the blockchain revolution, to reach a consensus in a decentralized and self-organized way, very much in the same way that happens in the natural world, naturally, by organizing themselves in reaching a high consensus state, but by dumping the entropy somewhere else through proof of work, we reach now a new era from centralization back to decentralization. So this brings me to the fundamental theme of my talk today. So if you want to build consensus, let me ask all of you in this audience, among all the creation of the human mind, of all human knowledge, about which branch of knowledge do we have the highest consensus about? No doubt, in my mind, it is the language of mathematics. So when you look at, on the left-hand side, we have these beautiful mathematical objects called Platonic solids. We admire them because of their mathematical depth, but also sheer beauty because of its symmetry. When I actually fashion a cube, I can never make a perfect cube. We can never agree in consensus way about a cube, because I will always make some mistakes in my effort to produce a perfect cube. But the mathematical cube as a concept is perfect and it's consensual. There's no doubt about what a cube is. And this is why Plato, the greatest Greek philosopher, idealized those 5 objects as the model for perfection. When we look at our physical world, the world, we are made out of atoms. The atoms are made out of elementary particles. As we try to describe the behavior of the most profound truths of nature at its deepest level, it is the beautiful set of equations of mathematics, which is the standard model on the right-hand side. So therefore, math has always been the language of the natural world. But humankind finally reached a new era in our civilization, where we can really build trust based on the most consensual part of the human knowledge, which is mathematics. So therefore, I will coin the slogan for a new era to be in math we trust. But just as I explained to you, math is actually the language of the natural world, of the creation, and in a sense, math is the language of God. So in math we trust, what are the mathematical primitives which will help us to advance this era into a great new collaborative era of human civilization. I list here, obviously, we already have private key encryption based on the beautiful mathematical concept of elliptical curve, cryptographic hash functions, zero-knowledge proofs, zk-SNARK and zk-STARK, the improved version of it, allows us to have data privacy, but still possible to have exchange through secure multi-party computation. One topic which has not been discussed so much yet at this conference is formal verification. I'm very bullish about this. Maybe this can give rise to an audit system of the smart contracts. And then homomorphic encryption, and DAG, the directed acyclic graph, with a very simple slogan that money grows on trees. I very much share the enthusiasm of Professor Dansang, about the symbiosis between blockchain and AI. So far, I think AI is a little bit broken. Why? Because AI needs data. All of us, through our behavior, are contributing to the data, but they're not monopolized by centralized platforms. And they, because of the nature of centralization, it's starving innovation in AI. So what is going to happen is the crypto economics will create a right incentive structure, so for those who contribute data can actually be rewarded. And once you have an incentive system, then you get a positive feedback loop. Then all of us will contribute more data because we can get rewarded or incentivized for it, and then AI will become smarter and may price the value of our data better. And that, I really think, is the opportunity for crypto economics to do social good. Because AI needs data, but all data are not created equal. What we need the most to get AI to be smart is to learn from the corner cases. Right now, if you have an image recognition program, which is already have an accuracy of 99%, in order to get the extra 99.9%, you need to understand all the corner cases. So those special cases, which are out of the norm, are most important. So this is a concept called mutual entropy. So therefore, in a fair data marketplace, the mutual entropy is exactly the right pricing mechanism for the valuation of the data. How valuable the data is. The more differentiated this unique data is from the rest of the data, the more valuable it is. So that gives us a wonderful opportunity to do wonderful social goods in this new era of the blockchain. Because those minority groups that have been discriminated in the fiat economy now gets most valued in the crypto data economy. Ugly duckling becomes a beautiful swan. It can also work in the other way. Not only blockchain can provide data through an incentive structure for AI to learn, it will also work the other way. AI can actually, one of the most serious problems we all talk about today is the problem on the blockchain that there's no natural compliance mechanism. But AI can actually watch over the blockchain in detecting those malicious behaviors. So I really come to the end of my talk. Here's my most favorite book among all books, which is Newton's Principia. By writing down the Principia, Newton laid out the foundation for us to understand the natural world. But if you get the spirit of my talk, we finally get into a new era where we actually, in the crypto economic world, the economic science, which is a little bit always viewed as a dismal science, cannot be a precise science, because the very fabric of the crypto economic world is based on mathematics. In mathematics we trust, we build a new economy, but also it gives us hints of the mathematical principles of this new crypto economic science. And finally, maybe we can realize a grand dream that not only we have the first principles of the natural world based on mathematics, but also for the crypto economic world. Thank you.